from magnetospheres to hemispheres and ionospheres. I would like to try to connect gravity waves, atmospheric gravity waves, Martian dust storms, and atmospheric escape on a very big picture level, and using a recently published article as a reference. So we know that gravity waves play an important dynamical and thermodynamical role in planetary atmospheres. They have been heavily studied on Earth and Mars, and there is an increasing amount of research about other planets as well, other terrestrial and exoplanets, possibly theoretical research about the role of gravity waves on other planets. So there's sufficient motivation to study gravity waves and their role in the upper atmosphere and ionosphere. One important process on Mars that influences its long-term evolution is the transport of water, and how such circulation of water in the atmosphere is connected to dust storms. Recent research in modeling as well as observation shows that there is an enhanced circulation of water and transport into the upper atmosphere on Mars during dust storms, especially during global dust storms. Now, this study is going to look at the aspect of gravity waves and how they could be connected to dust storms and loss of water on Mars. For this, we have analyzed carbon dioxide density fluctuations as observed by the NGIMS instrument on board NASA's MAVEN spacecraft. And we will do a first order calculation of gravity wave activity and the relevance influence of the relative influence of the changes in gravity wave activity on atmospheric gene escape. So significant gravity wave induced temperature fluctuations have been already documented in literature by models. Here you see at 3 different altitudes, 80, 100, 120 kilometers on Mars, a latitude, solar longitude variation of gravity wave induced temperature fluctuations, gravity wave induced acceleration and deceleration, what we call gravity wave drag, and probability of cloud formation. What you see here is the variability is extremely high, the variability in gravity wave activity. And these values of, for example, during perihelion in the southern hemisphere, temperature fluctuations exceeding 20 Kelvin are quite significant. There's an Earth analogy, of course. Gravity waves have been studied heavily in the last 10, 15 years in the thermosphere of Mars. So we are essentially exploiting this expertise from past experience and from past publications. On Mars, higher altitude gravity waves, so thermospheric gravity waves have been observed for the first time by MAVEN at really high altitudes, up to 220 kilometers, using, however, only a certain number of inbound and outbound orbits, since MAVEN had started to provide high quality observations of densities around late 2014. So that was an initial study which showed that the relative density fluctuations produced by gravity waves are in the order of 20 to 40%. And they kind of peak at around 200 kilometers and even slightly above that. The 2018 dust storm was quite spectacular because it was a planet encircling dust storm. And a publication in 2020 showed us how the latitude versus column opacity varied during this dust storm. As you can see, after the onset of the storm, the growth phase is quite intensive. It's rapid. Now the question is, how does the thermospheric gravity waves respond to such rapid variations during dust storms? Gravity waves can be quantified by looking at the density fluctuations represented by rho prime. And here you see an altitude, time or date variation, as well as solar longitude variation of gravity wave activity. Longitude as a function of longitude, latitude, as well as local time. The big picture shows that the response of the gravity wave activity to the onset to the dust storm is quite rapid. The onset of the dust storm can be associated with the period between 1st of June and 16th of June approximately. It takes about 2-3 weeks, and the gravity waves peak. The gravity wave activity peaks around 190 to 200 kilometers in the atmosphere. You can see that the nighttime gravity wave activity is larger than the daytime gravity wave activity. The longitudinal variation of gravity wave activity during dust storms is quite complex, and the latitude variation, the latitude coverage obviously varies because of the variation of the orbit. However, we can see that at low latitudes here, where the amount of dust is present during dust storms, the gravity wave activity increases significantly. So again, we are dealing with temperature density fluctuations up to 40% in a mean sense. Instantaneously, the density fluctuations can be even much more larger than that. It can easily exceed 100%. Now, how do we make sure that the dust, actually, the increase in dust has caused the increase in gravity wave activity? What we can do is by making sure we make an orbit to orbit and season to season comparison. And the best match we could find in terms of this orbital and seasonal configuration was 2016 period. It was a low dust period, and we have done a similar analysis of gravity wave activity. You can see the dust case clearly shows much larger gravity wave activity at low latitudes than the low dust scenario. So this gives us some confidence, quite a strong confidence, that gravity wave induced temperature and density fluctuations actually increase significantly because of the dust activity. Now, finally, coming to the connection to escape. The previous speakers have already documented some theory of atmospheric escape, such as Jeans escape. Here, the relevant parameter is obviously the flux, escape flux. And the escape flux is connected to temperature via the Jeans parameter that we have heard 2 speakers ago. And now we have to include in that temperature the gravity wave induced fluctuations. Through the density fluctuations, temperature fluctuations will occur. All thermodynamic parameters are interconnected, including this T prime, assuming a sinusoidally varying gravity wave harmonic. You can show that the flux, the increase of H flux, H escape flux, H meaning hydrogen, is up to a factor of 2.5 for an increase of gravity wave activity by 20%, and it is 5.5, so an increase, 5.5 times the increase in escape flux for gravity wave activity of 40% in temperature fluctuations. If the temperature fluctuation grows, then the relative escape rate increases as well. When we say relative escape rate, we mean a comparison with a case in which we do not include the gravity wave associated fluctuations. Overall, the escape and the positive phase of the flux is not canceled by the associated escape in the negative phase of the wave, as can be seen in this figure. Therefore, the net result is, although we deal with a sinusoidally varying wave activity, the net result is an increase in escape due to temperature fluctuations. Given that at exobase level and upper thermospheric level, gravity waves are continuously present, they will play an essential role in modulating escape, especially during global dust storms, which are quite regular meteorological phenomena on Mars, with varying intensity, of course. How many minutes do I have?
2 minutes.
Cool. So coming to the summary, I think it's necessary to put all this into a bigger context. First of all, atmospheric general circulation models have been showing us that gravity waves of meteorological origin on Mars continuously propagate into the thermosphere and ionosphere. And we see their signatures in observations. During dust storms, the situation is slightly more complicated because of the changes of the mean fields, meaning the changes in the circulation, ionization, stratification, and density. So the response of the gravity waves to the changes in the dust activity is rather strong and rather nonlinear, probably. The magnitude of the relative density perturbations are in the order of 20% on average and 40% locally during dust storms. And the estimated net increase of Jeans flux of hydrogen specifically is a factor of 1.3 and 2 for these scenarios of 20% and 40% gravity wave induced temperature fluctuations, respectively. Overall, larger wave amplitudes, larger wave fluxes imply in a warmer atmosphere during dust storms lead to quite unintuitive results, because in a warm atmosphere, lower gravity wave activity is expected. However, the opposite scenario occurs. There's an enhanced loss of hydrogen via Jeans escape process, and this will have an impact on water transport. The meridional circulation is strengthened during dust storms. That meridional circulation transports water vapor into the lower thermosphere and middle thermosphere, where water could be efficiently dissociated, and that dissociation produces hydrogen, which in this case, as we have shown, hydrogen is very sensitive to gravity wave activity induced escape flux. So gravity waves could have played an important role in the long-term evolution of the Martian weather and specifically Martian water. And this will have implications not only for Mars, but for Mars-like other planets as well, if you are thinking in the context of exoplanets. So for terrestrial planets specifically with intrinsic magnetic fields or with strong magnetic fields, let's say, the influence of gravity waves on escape is going to be much more complex than what we have discussed here, because gravity waves are influenced by ion friction. So gravity wave dissipation is connected to ion friction, and ion flow is connected to magnetic field configuration. Therefore, depending on the configuration, on the complexity of the magnetic field, gravity waves will encounter a slightly different dissipation and propagation characteristics in each case, probably in each scenario of planetary magnetic field. Thanks very much indeed.
Thank you. We're a very clear talk. You've got a couple of questions in the chat so far. So we've got Catherine Reagan asks, have you considered any other data from other instruments on MAVEN? They said that they're looking at the dust storm effects on electrons with MEX and the 2007 storm. So it'd be good to chat at some point.
I have not specifically looked at the ion data. I have intended to, and I'm really willing to collaborate on that. The focus was to look at the neutral atmosphere initially. However, as has been suggested by the question, ions and neutrals can be coupled. And we will have to look at, it would be interesting in general to look at the ion gravity wave signatures in ions as well. I have to say, even on Earth, gravity wave activity or gravity waves in the ionosphere are not as heavily studied as in the thermosphere. It's kind of an unexplored territory that would be interesting to work on that. And next.
Okay, and our next question is, do you think it's likely that the same increase in Jeans escape would occur for thermospheric higher frequency acoustic waves?
So I have a bit difficulty to hear you acoustically, but you mean on the role of acoustic gravity waves, what that could be, and in Jeans escape? Is that what you meant?
Yeah, so the question's in the chat if you want to be able to see it.
Yeah,
as well.
I have to stop to see it.
Yeah, sure.
Yeah, okay. So that's a fantastic question. The high frequency acoustic gravity waves, it's again an unexplored territory, study of acoustic waves on Mars. There are not, there isn't a significant amount of literature on that. However, what we know from basic theory and from Earth research is that high frequency waves are susceptible to back reflection. So there's a higher probability of those waves, acoustic waves, to be reflected and not reach really high altitudes. So that's one scenario, theoretical scenario. And models do not include high frequency acoustic waves, so we cannot learn about these waves. I have to say that non-hydrostatic models don't include them. There are non-hydrostatic models which would include them, so it would require such studies. In theory, the high frequency gravity waves could be separated from the others, but that would require a detailed analysis of wave spectrum in order to answer that question.